Now then, ladies and gentlemen, in this part of the lecture, we shall be studying about the properties of CTFT. And before proceeding to the properties of CTFT, we must modify the synthesis and analysis equation in the following manner. So what we need to do is we have to modify the synthesis and analysis equation in the following manner. Now, if we consider j omega to be equal to twice pi f or equal to capital omega, not j omega, just omega, then what we get is that if we take the derivative d omega over df, which is essentially equal to d of capital omega over df. Capital omega is nothing but another nomenclature for omega, that is the angular frequency in our case. This can be written as twice pi ddf of f. What we are doing is differentiating this term with respect to f. So twice pi being constant will come out of the differential operator, and ddf of f will remain as it is. Now, simplifying further, we multiply this df to the right hand side. We get d omega equal to d of capital omega twice pi d of f times df by df. This two obviously cancels out, and all we are left with is df to be equal to 1 over twice pi d omega, or 1 over twice pi d capital omega. So hence, replacing the value of df in the synthesis and the analysis equation, we get the synthesis equation to be equal to x of t equals to 1 over twice pi minus infinity to infinity x of omega e to the power j omega t d omega, and the analysis equation on the other hand becomes x of j omega to be equal to integral, which goes from minus infinity to infinity, x of t e to the power minus j omega t dt. So for the rest of the lectures, we shall be operating using these two equations. Now for the first property, which is the linearity property, we say that if the Fourier transform of any signal x of t be x of j omega and the Fourier transform of y of t be y of j omega, then according to the linearity property, what we will get is the Fourier transform of a of x of t plus b times y of t will give us a of x j omega, b y j omega. To prove it, say if z of t is equal to a x of t plus b y of t, then the Fourier transform of z of t, which is capital Z of j omega, to be equal to minus infinity to infinity z of t e to the power minus j omega t dt, which is written from the direct transform equation. Direct transform equation. Now, replacing the value of z of t, we get minus infinity to infinity ax of t plus by of t e to the power minus j omega t dt. Now, as per the property of integration, we can divide this in two parts, which were a times minus infinity to infinity x of t e to the power minus j omega t dt plus b minus infinity to infinity y of t e to the power minus j omega t dt. Now, upon closer inspection, this term is quite similar to this part of the equation. So, instead of this integral, we can write it to be equal to a of x times j omega, plus similarly this term is also similar to this term, and this can be written as b of y of j omega. So hence the Fourier transform z of j omega becomes a x of j omega, b y of j omega. So what I mean to say is that if we take the Fourier transform of z of t, that is this part, we end up with this transform equation. Now, moving on to the next property, which is the time shift property. The time shift property, where if any signal x of t has a Fourier transform of x of j omega, then if x of t is shifted along the time axis with a value of t naught, so x becomes xt minus t naught, let it be equal to z of t, will give us the Fourier transform, that is z of j omega, to be equal to x of j omega e to the power minus j omega t naught. That means if we shift a signal along so what I was saying is, if we shift a signal along the time axis, the Fourier transform will remain as it is, although being multiplied by a factor, that is e to the power minus j omega times the value the signal has been shifted. So if we are to prove it, we can write z of j omega equal to minus infinity to infinity x of t minus t naught, that is this value of z of t e to the power minus j omega t dt. Now if t minus t naught equal to m, suppose t minus t naught equal to m, then we get t to be equal to m plus t naught. And if we take the differentiation, we get dt over dm to be equal to dm over dm plus ddm of t naught. Now since t naught is a constant value, because we can shift any signal, say for this signal t to 1 to t naught, and this value will always remain constant. So this becomes 0 and this becomes 1. So we get dt to be equal to dm. Now when t goes to infinity, so if t goes to infinity, then subtracting a value from infinity doesn't change the value of infinity, it rather remains as infinity. So m will also be equal to infinity. Again, when t goes from negative infinity, m will also go to negative infinity. Now from this concept, if we change the integral, we get z of j omega to be equal to m, which goes from minus infinity to infinity, x of m e to the power minus j omega, t becomes m plus t naught, and dt becomes dm. Now, upon further simplification, we can dissolve this part into two separate exponents, e to the power minus j omega m and e to the power minus j omega t naught dm. So evidently this part is also what should I say, a constant, because t naught is constant, omega is obviously constant, and j, which is the imaginary number root over minus 1, is also a constant. So we can take this value out of the integral, and this becomes e to the power minus j omega t naught m, which goes from minus infinity to infinity, x of m e to the power minus j omega m dm. Now this part is, as we have seen before, quite similar to the direct transform equation, and hence this part of the equation can be written as x of j omega. Of course, this part will be multiplied as well as j omega t naught. So we have established that the Fourier transform of this signal is this one. So from the time shift property, we can write x of t minus t naught, where a signal is shifted by a value of t naught, will give the Fourier transform pair e to the power minus j omega t naught x of j omega. Now moving on to the next property, which is the frequency shift property. Which is quite analogous to the time shift property. Here, as before, if we consider x of t to have a Fourier transform of x of j omega, then suppose z of t be another function which is equal to e to the power j beta of t times x of t. Now in order to determine the Fourier transform of z of t, we get capital Z of j omega to be equal to, from the direct transform equation, minus infinity to infinity z of t e to the power minus j omega t dt. Now what is the value of z of t? We simply replace it to this one, e to the power j beta t times x of t e to the power minus j omega t dt. Now multiplying these two parts of the equation, minus infinity to infinity, x of t remains as it is. We take e to the power common, e to the power minus j omega minus beta t dt. Now comparing it with the direct transform equation or the analysis equation, it is quite similar, where z of t is replaced by x of t, e to the power remains as it is, minus j is minus j, dt also remains same. This t operator inside the power of e will also remain same. What essentially has changed is the value of omega from omega to omega minus beta. So this gives the Fourier transform to this value will give us the Fourier transform of z of j omega. Similarly, this will also give the Fourier transform of x of j. Instead of omega, since it has been changed to this value, this becomes omega minus beta. So what you have seen is that if we shift the frequency, if we shift the value of the signal in the frequency domain, the time domain value becomes equal to this one. So we can write x of t e to the power j beta of t will give us a Fourier transform pair x of j omega minus beta. So essentially what it means that if we shift a value of the signal in the frequency domain by a value of beta, in the time domain the exponent e to the power j beta t is multiplied to the original signal. Now moving on to the next property, which is our scaling property. The scaling property, where, say, as before, if x of t is a Fourier transform pair of x of j omega, then we consider z of t to be equal to x of at, where z of t is nothing but a scaled version of x of t with a scaling multiple of a. So from the analysis equation, the Fourier transform of z of t, that is z of j omega, will be equal to minus infinity to infinity z of t e to the power minus j omega t dt. Now replacing the value of z of t by x of at, we get minus infinity to infinity x of at e to the power minus j omega t dt. Now similarly, if we consider as before at to be equal to m, then we get dt equal to dm by a, and obviously from here we get t equal to m over a, and when t goes to infinity, then m will also go to infinity, which means that if t goes to infinity, so multiplying infinity by any number will also result in infinity. And similarly, when t goes to minus infinity, m will go to negative infinity. So, changing our new integral operators, we get z of j omega to be equal to m, which goes from minus infinity to infinity, x of m e to the power minus j omega. Instead of t, we write down t to be equal to m by a, and dt becomes 1 over a times dm. dt is equal to 1 over a times dm. Now then, moving forward, since 1 over a is a constant value, we bring it outside the integral, we get 1 over a, m goes from negative infinity to infinity, x of m e to the power minus j omega m by a dm. So, upon closer inspection, this part is similar to the analysis equation over here, where the time is changed from t to m by a. So, z of j omega will become 1 over a, x of j, instead of omega, we get omega by a. So, from the scaling property, we can write xa of t has a Fourier transform pair that is equal to x j of omega by a. Moving on to our next property, which is the frequency differentiation property. The frequency differentiation property, where if x of t is a signal and gives the Fourier transform pair of x of j omega, then we can write x of j omega to be equal to minus infinity to infinity x of t e to the power minus j omega t dt, which is the direct transform of the analysis equation. And what we are going to do now is differentiate both sides of the equation with respect to omega. So the left hand side becomes dx of j omega over d omega equals to minus infinity to infinity. Since x of t is not dependent on, that is omega, we can write it as it is, and the rest of the equation will be differentiated. Now, moving forward, the right hand side remains as it is here. The left hand side remains as it is. In the right hand side, x of t will remain same, and differentiation of e with respect to omega will give e to the power minus j omega t. That means differentiation of e of what I mean to say is that differentiation of e to the power minus j omega t with respect to omega will give the value as before. And this is the formula of differentiation of e, and we differentiate the exponent of e, that is minus j omega t, and this will give the value of minus jt dt. We have done simple differentiation from this part to this part. Moving forward, we rearrange the equation of minus infinity to infinity x of t times negative of jt e to the power minus j omega t dt. So what we are going to do now is the right hand side, that means this function overall will give us a Fourier transform of this function, since along with the integral and e to the power minus j omega t dt, this resembles the direct transform equation. So if we take the Fourier transform of this function, we get this value. Hence we can write minus j omega t minus jt x of t will give a Fourier transform pair of d omega of x of j omega, which is essentially the frequency differentiation property. Now then, moving on to the time differentiation property, to the time differentiation we get, say x of t is a function and its Fourier transform pair is x of j omega, then rather than the direct transform, if we use the inverse transform or the synthesis equation, x of t can be written as 1 over twice pi minus infinity to infinity x of j omega e to the power j omega t d omega. Now differentiating both sides as before, with respect to time in this case, since the property dictates time differentiation, this becomes ddt of x of t equals to 1 over twice pi minus infinity to infinity, and since x of j omega is not dependent of time, so we can write it outside the differentiation operator, and this goes as ddt of e to the power j omega t d omega. Okay, moving forward, minus infinity to infinity x of j omega remains as it is. If we differentiate e to the power j omega t with respect to dt, we get e to the power j omega t, and differentiating the according to the chain rule of differentiation, j omega t with respect to dt, we got j omega, and d omega remains as it is not dependent on time. So then, rearranging a bit, we can write 1 over twice pi minus infinity to infinity x of j omega times j omega e to the power j omega t d omega. Now, again, if we look closely, the inverse transform of this function, the inverse Fourier transform of this Fourier transform pair is nothing but this value. So, on the contrary, we can say that if we take the Fourier transform of ddt of x of t, we will get this value as this equation 1 over twice pi, an integral goes from minus infinity to infinity e to the power minus j omega t and d omega, is quite similar or analogous in the nature of the synthesis equation as mentioned over here. So simply we can write d dt of x of t is the Fourier transform f of t, which is j omega x of j omega. So moving on to the convolution property. The convolution property dictates if x of t gives us a Fourier transform pair of x of j omega and y of t gives us a Fourier transform pair of y of j omega, then suppose z of t to be equal to x of t convoluted to y of t. So from the direct transform of the analysis equation, z of t can be written as z of j omega t, which goes from minus infinity to infinity, z of t e to the power minus j omega t dt. Replacing the value of z of t, we get t which goes from minus infinity to infinity, x of t convolution of y of t e to the power minus j omega t dt. Now, as per the basic rule of convolution, the basic formula of convolution, we can write x of t convolution of y of t to be equal to tau, which goes from minus infinity to infinity, x tau y of t minus tau d tau. So, replacing this value in this equation, what we get is that z of j omega equals to t, which goes from minus infinity to infinity, and tau, which goes from again minus infinity to infinity, x of tau d of t minus tau d tau, and the rest of the equation e to the power minus j omega t dt. Now, rearranging a bit, as we have said before, if we interchange the integrals in any double integral operation, the outcome remains as it is. So we can take this inner integral in the outside where tau goes from minus infinity to infinity, and x of tau, since it is not dependent on t, we can bring it out as well. So x of tau t, which goes from infinity, negative infinity to infinity rather, y of t minus tau, I'm sorry, this will be y of t minus tau e to the power minus j omega t dt d tau. Now, if t minus tau equals to m, so t equals to m plus tau, and similarly dt will be equal to dm, and as you have seen before, when t goes to infinity, m will also go to infinity. T when goes to negative infinity, m will go to negative infinity. So changing this equation with the new variables, we get tau, which goes from negative infinity to infinity, x of tau, m, which goes from negative infinity to infinity. Remember, the new variable is m, which replaced t in the earlier part of the equation. y of m e to the power minus j omega m plus tau dm d tau remains as it is. Now, moving forward, we can write z of j omega to be equal to tau, which goes from minus infinity to infinity, x tau, and separating this part of the equation and taking e to the power minus j omega tau out, e to the power minus j omega tau, and taking this d tau along with it, and we can write the rest of the equation. M, which goes from minus infinity to infinity, here remains y of m e to the power minus j omega. Since we have taken out tau earlier, all we are left with is m, j omega m dm. Now then, this part and this part are nothing but the analysis equation of the Fourier transform, and hence this can be written as x of j omega times y of j omega. So what we have established is that x of t, when convoluted to y of t in the time domain, in the frequency domain upon Fourier transform, we get the Fourier transform pairs to be multiplied. So with this property, we come to an important realization, which is very much important in all regards or all aspects of the digital signal processing or signal analysis, and must be remembered throughout the course, is that if we convolute a signal in the time domain, the Fourier transform, or in the frequency domain, the values will be multiplied. And the converse is also true. That means if we multiply a signal in the time domain, in the frequency domain, their values will be convoluted. I hope that is clear. With that, let us move on to the next property, which is the one of the most important property, that is the duality property. The duality property.